Hello, welcome back to Organic Chemistry. My name is Todd Rothman. In this video, we're going to go over hybridization. Now, I hope at this point that you have a good enough understanding of quantum mechanics, you understand the wave properties of orbitals, and all the things that we discussed in the previous video. You know, obviously, we did a little bit of a story. We built up to the point of hybridization, or I should say, just orbitals in general, and now we're going to actually apply it to the ideas of hybridization. Okay, now, just like with the quantum mechanics, there's two things we're going to do here. The first thing is we're going to go through a philosophical understanding of orbitals. You need to get this, okay? Because, like I said before in the previous video, this material is going to come up over and over again. And if you just memorize a simple way of figuring out hybridization, it's good in the terms of maybe doing well on this exam, but it's not good for the whole course, okay? So you really do need to have an understanding as to why things are the way they are, how does hybridization work, and so we're going to spend time doing that. Then we're going to go into the tricks. So if you look at over here my numbering, number 6 says the simple method for determining hybridization, and we're going to get to that. And you're going to see it's very easy, it's a simple thing to figure out, but the philosophy we must go through first. All right, so that's what we're going to do. These are the topics. Let's get started. So the first thing is, what is hybridization? Well, hybridization is a mixing of orbitals together. So when an atom, or let's say two atoms, are going to come together and make a bond, one way that they could do that is that they can actually, they can actually have their s orbitals combined to make a new bond, or they could have their p's come together and make a bond, or they could both prepare beforehand, mix up their s's and p's, and then come together to make a bond. When they mix up their s's and p's, or even d's, but in our case we're going to focus on s and p only for organic chem, that is called hybridization. It's the mixing of atomic orbitals getting ready to make molecular orbital. Okay, and then the molecular orbital that combined is a hybridized orbital at the end. Okay, so let's take a look at why we would do this. So the question here is very simple. It says, how do we know hybridization occurs? We can't see orbitals, right? We can't really do much experimentation on them to know that this occurs, but we do know it happens. And so what we do is we have indirect information that we use to figure out that this is actually taking place. And here's an example. If we look at, let's say, a methane, a carbon that has 4 H's around it, the first thing we have to consider is, with carbon in its ground state and hydrogen in its ground state, can they actually make a bond? Well, when we look at the ground state of carbon, so here's my little diagram on the left, and what we really care about are the valence electrons, right? We don't really care about the 1s as much as the 2s and the 2p. Notice that when you fill in these electrons, carbon has 2 electrons in its p's that are ready to take 2 new electrons in. Remember, each orbital can have only 2 electrons. So if carbon has 2 electrons, 1 on each p, then both of those p's can make bonds to some other atom that would bring an electron into that slot, right? So here's a pictorial diagram of this, where we have right here, these are the 1s electrons. Now these are the 2s, and I want you to notice something. The 2s is a little bit closer to the nucleus than the p's. This is px, let's say, and py. Now it turns out that this is true. When you're looking at the s orbital versus a p, the s is closer to the nucleus in the same shell than a p would be. Okay, and we'll come back to that at the end of this video set. So anyway, here are my 2 p's. Now notice that carbon right now, as it stands, can have 2 electrons come into those positions, and then they could become molecular orbitals. Right now this is an atomic orbital, right? So the other thing to note is that there is a p over here that's empty. There's nothing here. There's no electrons in it, right? When you look at the diagram on the left, there's this empty orbital. Let's say this is x, this is y, this is z. Well, z has no electrons in it. So it can't make a bond there. It can't do a covalent bond where it brings an electron to the table, right? Because it has no electron there. So as it stands right now, this carbon could make 2 bonds, but it can't make 4. Not like this. Okay, H, we have no problem. The ground state of H, you have one electron, so sure, it can go in, and carbon's one electron can go in the middle, and they can make a bond. So carbon, right now, as it stands, is the problem, not hydrogen. Hydrogen has an s orbital ready to go. It could bond with whoever's willing to come up with an electron, right? But carbon's the problem. So here are the questions that we're gonna face and we're gonna answer. The first thing is, can hydrogen make a bond? The answer is yes. We know that it can. I just explained it to you. Can carbon make 4 bonds? No, not in its ground state. It can make 2 bonds. It could make a 3rd bond if someone was willing to give 2 electrons and put it into carbon's empty p orbital, but it can't do it by itself. So this is where we have to come up with the workaround. So this is the basic framework that made us realize, chemists realize, that there's an issue. There's something more to the story. Carbon in its ground state will not do the job. So we go on with our story now. The first thing we're going to do, A, is we're going to excite the electron that carbon has. One of those p electrons could be actually, the 2s electron could be excited into the p orbital. So let's take a look at how that works. So here we have this red electron. Now, by the way, I'm at this point showing you the 1s, but we could just ignore it. Remember, bonds occur with the valence electrons, the outermost shell. So it's really the 2s and 2p that we're worried about. So this 2s has 2 electrons in it. That's the normal way ground state electron configuration, right? But now, what if I was to give it energy where it can take that electron and put it up into this empty orbital? Well, when you do that, this is energy. We need energy to do this. And when you have that energy, and the system could provide that energy, then that electron can go up into the higher energy state. This is called the excited state. Now, here's the thing. Once we do that, once we take a 2s and bring it over into the 2p that's empty, well, now look at carbon down below. So what I did was, here's my 1s. We just ignore that, right? This is the 1s. Now, look what I did. Now I have this, let's say, is the 2s. It's a little closer than the other ones. All of a sudden, 2px, py, and pz all have 1 electron because we excited the carbon into its higher energy state. This carbon can make 4 bonds because now it has 1 electron in 4 orbitals, and 1 electron from other atoms can go in and make a bond there. So can this work? Yeah, now we are good to go. We can allow carbon to make 4 bonds by just making it go into the excited state. But here's the problem. The problem is that when you look at carbon, like when we look at methane, it turns out that methane, every length, the bond length in all 4 cases to H's is exactly the same. They're not different. They're all the same length. Atoms have this all the time. When an atom makes a bond, if you look at any of its bonds, they're the same length if it's the same bond type. But even actually, well, no, let's leave it at that. So single bonds on the same atom are all the same length for that molecule. Okay, so this right here is not going to meet the data that we have. Our little pictorial diagram here doesn't allow us to realize this right here, what I just said. They're all the same bond length, but the diagram I showed you is not. And you're saying, well, what do you mean? Why is it not? Well, here's the story. Think about the fact that there's 1 electron in the 2s orbital, and the s is a little closer to the nucleus. So what really would happen here, what this would equal, is a carbon that has 3 p orbitals, so they'll be the same length to H's, right? Let's say this is the px, py, pz becoming a molecular orbital. So these are molecular orbitals, but you get the idea. Carbon's contribution is its px, py, pz. Well, they're all the same length, but there's 1 orbital, the 2s. It's going to be a little closer to the carbon. So this one should be a little shorter. This would be shorter, and these would be the same length. Well, we don't see that here. We don't have...